Hey guys, Mr. Backerberg here. In this video, we're going to look at accumulation problems as area. Now, before we actually get into looking at area, I want to take a look at this problem. So say we've got a ship moving along the ocean at a steady rate of 7.5 nautical miles per hour, or knots, from 7 a.m. to 9 a.m. We want to find the distance traveled by the ship. Now, because we're looking at the distance traveled, we can use the formula distance equals rate times time. We know that our rate is 7.5 nautical miles per hour, so I'm going to fill that in for the R value. And our time, well, we were going from 7 a.m. to 9 a.m., so that's 2 hours. So if we multiply these together, then we can say that our distance covered is 15 nautical miles. But now what we're going to do is try to put a little bit of a calculus spin on things. And what we're going to do is try to connect this distance formula that we just used to the graph of a velocity function. So same exact problem, but we're looking at it through a little bit of a different lens. So our ship is still moving along the ocean at a rate of 7.5 nautical miles per hour, and we're still going from 7 a.m. to 9 a.m. And we want to find the distance traveled by the ship. But here's what we're going to look at. We're going to look at our velocity function. Now, because we're going at a constant rate of 7.5 nautical miles per hour, then we can say that our velocity at any given time is just 7.5. So that's where we're getting this flat line at 7.5. We've got a constant function, so it's a flat horizontal line through that specific y value. And if we're graphing this compared to time, we're looking at it specifically between 7 a.m. and 9 a.m. So what's actually happening in here is as we're taking a look at this rectangle, the distance that we're covering is directly related to the area of this rectangle. We've got a height of 7.5 since we're getting up to that y value of 7.5. And our distance across the bottom here, we're going from 7 to 9, so that's a distance of 2. So if we were to find the area of this rectangle, we would get 15, which we just said was the distance that we had covered in these 2 hours. So there is a direct relationship to that distance formula that we used before compared to looking at the area of this rectangle that's representing our velocity being compared to our time. Now that worked out nicely because we had a rectangular region which is easy to calculate the area of. But what if the ship had a velocity v that varied as a function of the time? So instead of just being a flat constant velocity, now our velocity is changing. So now it's not quite as straightforward as to how to calculate the area. Now, the creators of calculus wondered if this area, even though it's an irregular region, would still give the total distance traveled over that time interval. And they thought it would, and that's what led them into the idea of finding a calculus which is going to allow them to find the area underneath specific curves. And what they thought about doing was taking this area region underneath the curve and splitting it into small sub-intervals, which if they went small enough, then each one of those sub-intervals would look almost like a rectangle. And then as we're dealing with those rectangles, it's much more straightforward and easier to calculate the area of a rectangle versus a curved region. So as we keep slicing these regions into smaller and smaller chunks, then each chunk starts to look more like a very narrow rectangle. And then what the creators of calculus thought was that once we have this partitioned up into all of these different rectangles, we could just add all of their individual areas together to give us the total area underneath the curve. So in this example, let's think about a snowstorm that starts at 3 a.m. and over the first 2 hours, the rate of snowfall increases from 0 to 1.2 inches per hour. And then for the next 3 hours, it continues at a constant rate of 1.2 inches per hour. Then at 8 a.m., it begins to taper off and it decreases at a steady rate until the snowfall ends at 10:30 a.m. We want to figure out the total amount of snow that falls during this snowstorm. So we're going to think about this graphically. So we've got a snowstorm starting at 3 a.m. So across my horizontal axis, I'm going to say that this line right here represents 3 a.m. And we said for 2 hours, the rate of snowfall increases from this rate of 0 up to a rate of 1.2. So this vertical axis is going to represent the rate of our snowfall. So we're going to start at 0 and we're going to go up for 2 hours until we hit a rate of 1.2. We'll say that's happening right here. So that happened for 2 hours. So now at this line, we're going to call that 5 a.m. Then for 3 hours, it was a steady rate of 1.2. So this horizontal distance is 3 hours. So now we're at 8 a.m. And then it says at 8 a.m., it began to taper off at a steady rate until 10:30 a.m. when it stopped snowing. So over here, this will be 10:30 a.m. And we're going to use this picture to help us try to determine how much snow fell during the snowstorm. And what we're going to do is break this up into shapes that are easy to calculate the area of. So if I draw in a vertical line at 5 a.m. here, we've got ourselves a triangle on the left-hand side. We know how to calculate the area of a triangle. If I do the same thing on the right-hand side at 8 a.m., then I've got another triangle. And in the middle, it looks like we've got some sort of rectangular shape. So what we're going to do is find the area of each piece individually and then just add all of the areas together. Now looking at this first triangular piece, across the bottom, that horizontal distance is 2, and then this vertical height takes us up to 1.2. So if I want to calculate the area of that triangle, then I would do 1/2 times the base, which is 2, times the height, which is 1.2. Well, 1/2 times 2 is 1, and then 1.2 times 1 is just 1.2. Now, as we look at this rectangular piece in the middle, that horizontal length across the bottom would be 3, and again, vertically there we've got this 1.2. So to find the area of that rectangle, I would take 3 times 1.2, which is going to give me 3.6 for that middle chunk. And then on the right-hand side, we've got another triangle. This time the distance across the bottom is 2.5, and the vertical height is still 1.2. So now for the area of that triangle, we're going to do 1/2 times 2.5 times 1.2. And if I multiply all that together, then I'm going to get 1.5. And then finally, adding up each of these individual areas, we're going to get 6.3. Now, we were talking about how many inches of snow were falling, so this 6.3 represents the inches of snow. That's going to be it for this video. Thanks for watching.